In this video, we're going to talk about correlation, dependence, and statistical estimation. So, just to remind you, what are independent events? Independent events are events such that if you take the probability of the intersection of A and B, it's equal to the probability of A times the probability of B. And based on that, independent random variables are random variables such that for any possible value of x and possible value of y, we have that the probability that x equal x and y equal y is equal to the probability that x is equal to x times the probability that y is equal to y. So, as an example, here is a table, a joint distribution table that gives us the probability for each one of the joint events for these two random variables, x and y. And we calculate the marginal probability here on the margin. And then we check to see if 0.2 times 0.4 is indeed 0.08, and it is. And again, we check for each one of these entries to make sure and see that these two random variables are indeed independent. And here is a dependent case where you have, again, the marginal distributions, but if you multiply 0.4 times 0.6, you get 0.24, which is not 0.3. Okay, so here the two random variables are dependent. On the other hand, covariance is a single number. Okay, so unlike dependence where we have to check all joint probabilities, covariance is a single number, and it's a number such that if the covariance is not zero, that implies that x, y are not independent or are dependent. But on the other hand, if the covariance is zero, that doesn't imply that x and y are independent. They can be dependent even though the covariance is zero. The correlation coefficient is simply a scaled version of the covariance, and where we divide the covariance by the square root of the variance of x times the variance of y. And therefore, the covariance depends on scaling, but the correlation coefficient does not depend on scaling. And the correlation coefficient is always between -1 and 1. So we tend to think about covariance in terms of the correlation coefficient, which is doesn't depend on the units with which we measure these two random variables. So here are some examples again. Here we have two correlated variables. So it's either if x is equal 1 or 2, then y is equal 1. If x is equal 3 or 4, then y is equal 3. So that's a correlation. And in this case, we have an anti-correlation. And here we have a situation where we have two independent random variables, so x1 and so x and y are all independent random variables, but the covariance necessarily in this case would have to be 0. Okay, so the next case, which is the interesting one, is where we have no correlation, but the two variables are dependent, right? So you can check that indeed the covariance here and the correlation coefficient is 0, but these are clearly dependent because these zeros would not be there if they were independent. So now let's look at a little bit of a bigger picture. Let's look at correlation and dependence when our distributions are continuous distributions. So our random variables have a continuous distribution. So in this case, we can plot the density function as a two-dimensional function. So we have the values of x in one direction, the value of y in the other direction, and the density of xy as this shape in 3D. Okay, and when the two variables are independent, what that means is that the columns or the rows are basically multiples of each other. So what we have here is that the that all of the red rows are similar, have the same shape up to a constant from the other rows, and same with the columns. Okay, so that shows independence. Here we have two-dimensional normal distribution where the the x-axis and the y-axis are independent normal distributions. And so what we get is a distribution which is, again, has covariance 0. Here, on the other hand, if we take the distribution to be something that goes at an angle to either axis, then even though this is the same distribution as before, by the fact that it's angled like that, we get that the two random variables are dependent. And here we have another dependence, which is basically that if you give me x, I get the value of y. And here is a case where the two distributions are clearly dependent, but the covariance is 0. Okay, so all of that is good and well, but what it means in terms of doing statistics is important. So what we're looking at here is, again, joint distribution table, but here it's really the joint counts table. So we're assuming that we're getting 400 samples, and we're counting how many of these samples falls in each of these places. Okay, so this distribution is very similar to the 1 quarter, 1 quarter, 1 quarter, 1 quarter that we had before, but the ratios are not exactly a quarter. So can we decide if this distribution is dependent or independent? Well, we'll see how to formalize it later, but intuitively we can say this is very, very close to the distribution that would arise when they're independent. On the other hand, suppose that we have 400 samples, and now x can go from 1 to 100, and y can go from 1 to 100. So we have basically 10,000 cells here. So just from that fact, it is likely that most of the cells, even if they have non-zero probability, will have 0 count, right? So most of the cells will be 0, there'll be some 1s, and maybe rarely we will see 2, okay? So in this kind of situation, which is not atypical, can we say that x and y are independent? No, we probably cannot say anything about that because we don't have enough counts in each location to basically be sure whether the product of the margins is equal or close to equal with the value itself. On the other hand, can we say that x and y are correlated? That we might be able to answer because we can calculate a single number from all of these entries, and that number will tell us if there is a significant correlation or not. Okay, so when we have something that is happening in continuous distribution, things are even more extreme. Here we have some examples of positive correlation, strong positive correlation, some positive correlation, negative correlation, and this seems like no correlation. Now, in any one of these cases, it would be impossible for us to say whether the two distributions are independent or dependent, right? Because whatever cell we put this in, there's going to be at most one example in that cell, and so we will not be able to say whether there is the probability that would arise from independence. So in this case, we are limited in continuous distribution. We're limited to answering only questions about correlation versus no correlation. Okay, so to summarize, correlation implies dependence. Dependence does not necessarily imply that there is correlation, but The advantage of correlation is that estimating correlation from data is much easier than estimating dependence. So next time we will talk about dependence, correlation, and causation.